Great. Thank you, everyone, for joining us today on a topic we're pretty excited about. A new feature for our SNAP PAC systems is the SNAP PAC redundancy option. So I'm going to go over several parts of this redundancy option that we offer from Opto 22. We've been actually offering it for about the first half of the year. Let's talk a little bit about what our objective was before we get into the details. First of all, naturally, anytime you're talking about redundancy, it's really about providing a method to increase system reliability. Now, naturally, and for people who are familiar with Opto 22 and our SNAP PAC systems, and of course dating back all the way to Mystic, our system architecture has always been inherently reliable, and that's how Opto got its name and its reputation, but also in the manner in which that we've built our systems or architected our systems. And by that I mean we've placed a lot of processors within a system. So you have a controller processor, naturally, you have processors in your I/O systems as well. And so to a certain degree that inherently provides a level of reliability you might not find in a traditional PLC system, where it's normally a single CPU combined with essentially remote dumb I/O that's not processed. So aside from that, we still had a request from many who were looking for a way to implement a controller-level redundancy, and again, to remove that single point of failure that may occur at a controller level. So we're also seeing worldwide many RFPs or requests for proposals for systems that offer an option for redundancy. And so that was really our objective moving forward. So our approach was to certainly respond to those objectives and requests, but also to set ourselves apart from others that offer redundancy in the marketplace. For example, we've added redundant functionality to our existing off-the-shelf controllers. In contrast to, say, our competitors or, say, other PLC systems, we don't require you to buy a specific redundant PLC or controller. We use our standard controllers and apply a redundancy option kit to that system to create a redundant system. So we also use standard PAC Control, PAC Control Professional, version 9, and standard Ethernet networking. Again, in contrast, we don't necessarily require you to build special cables or purchase special cables to create a redundant system. And then finally, because of the way we're able to put redundancy into the SNAP PAC system, it gives you a lot of flexibility that you wouldn't find with a normal system. And by that I mean there's many ways to construct your system, to download new strategies to your system, and each of the controllers can be active or backup at any given time. So you have a lot of flexibility in terms of how you build your redundant system. And these options typically exceed anything that you might find on a PLC. Okay, let's take a look at some of the redundancy requirements. The hardware required first. The first thing you're going to need to build a redundant system is a couple of PAC S-series controllers. This redundancy system is only supported by PAC S-series controllers today. That's PAC S-series 1 or 2, or the S1 or S2 in the wireless versions. The second thing you'll need is some I/O, naturally. SNAP PAC Ethernet I/O is what's supported on our redundant systems. Serial I/O is not supported. When you use the SNAP PAC Ethernet I/O, you have a number of options. You can use R1s and R2s as I/O, which is what I'll be doing today, or you can use EV1s or EV2s, and of course, wireless is also supported. The third part you'll need is the SNAP PAC redundancy option kit, or the SNAP PAC-ROK, and that's comprised of a number of components, which I'll get into now. The contents of the SNAP PAC-ROK, and for your information, there's the part number for ordering the SNAP PAC-ROK, is one, the SNAP PAC SRA, which is a standalone arbiter, standalone piece of hardware. The second is the SNAP RPSW, which is a power supply switcher. The third, of course, is a user's guide, which is a configuration, programming, virtually everything you'll need to know to get started with a redundant system. And then finally, you're going to need in PAC Project Professional version 9. And within PAC Pro 9 is a PAC Redundancy Manager. It's a software tool that allows you to configure the system, to commission it for redundancy, and then once it's up and running, to monitor and maintain that system. Okay, let's get into the details of each of those components. The first is, of course, the arbiter. The purpose of the arbiter is it arbitrates and determines which controller is the active controller and which is the backup. And it does that by communicating to the controllers via a dedicated RS-45 serial link, 2-wire. And essentially the arbiter sends out heartbeat requests and waits for responses from each of the controllers, and then it arbitrates who is master, or I should say who is active and who is backup. The other thing that the arbiter does is, based on these responses it gets from the controllers over the serial link, it can also manage the firmware and control strategies. And that's very important because as you as you commission your system, you need to make sure the two controllers are identical, not only from a strategy perspective, but also from a firmware side. So the arbiter has an ability to instruct each of the controllers to synchronize both their firmware and their strategies, and that's before the system even gets up and running. The arbiter also includes an Ethernet port. This port is typically used to monitor the system. So the redundancy manager uses the Ethernet port to communicate with the arbiter. It's not required, but it's certainly usually used. And finally, the arbiter allows a method to reset the controllers. For example, if you upgrade firmware in an Opto 22 controller, one of the next steps you need to do after the firmware has been installed is to reboot the system. So the arbiter has a capability of doing that through the SNAP RPSW, which is the remote power supply switcher. Now, this isn't a power supply. It's simply a power supply switcher. And so it's connected to the arbiter and to both controllers. And then this switch responds to the supply voltage output from the arbiter, which allows it to reliably restart a controller. So again, this is used to recommission a controller after its firmware has been updated. But it also gives you some other flexibility. For example, remotely rebooting a controller, say through PAC Redundancy Manager. On the side there, you'll see a bit of a wiring diagram that just illustrates that in a system that has 2 PAC S controllers and an arbiter, you will have 3 power supplies. So the arbiter can switch the power to the 2 different controllers, and then of course there is power supply for the arbiter itself. Okay, the final part is the SNAP PAC redundancy, in the SNAP PAC Redundancy Option Kit is the Redundancy Manager. Now, the Redundancy Manager is a piece of software that's similar to PAC Manager in many regards, but of course is specific to the redundant option. So this allows you to assign IP addresses like you might do with PAC Manager, install firmware, give you access to the PAC terminal software, and also allow you to manage memory. It also provides a pretty neat function called System Checkout. This is important because as you wire up your system and apply power to the arbiter and to the remote power supply switcher and to the controllers, this will go through and test all of those connections for you. If there's a problem at all with the system, it'll indicate that with a red X, meaning you need to go back and take a look at what may be wrong. The third part is, of course, commissioning. So once a system is configured within the PAC Redundancy Manager, you'll then go on to a commissioning phase, which essentially sets up the controllers, sets up their serial ports to talk with the arbiter, and also sets up anything in the controller to accept a redundant control strategy. Finally, once all those steps have been completed, monitoring and maintenance is performed with the SNAP PAC Redundancy Manager. So system overview, as you can see on the screen now, gives you an indication of what the current status of the system is. So in a SNAP PAC redundancy layout with all the pieces kind of put together, the first thing we see is a PC with PAC Project Pro 9, specifically PAC Control Professional 9.0. Version 9.0 has the option in the strategy options to enable redundancy. The second part is an Ethernet switch. So like most of our systems, there's an Ethernet switch. We recommend using a managed switch or at least a non-managed switch. Never use a hub. Next is 2 SNAP PAC S-series controllers. My illustration is indicating 2 PAC S2 controllers. S1s, of course, are supported as well. Then you have Ethernet I/O. In this case, we're using a SNAP R-series PAC as Ethernet I/O, and I will be using that in my demo as well. Finally, the Redundancy Option Kit, SNAP PAC Redundancy Option Kit. That's, as I indicated earlier, includes the arbiter, the power supply switcher, the user's guide, and then that combined with PAC Pro 9 will allow you to access the Redundancy Manager software. And then finally is wiring it all up. You can see a kind of a mix of wires of Ethernet, serial, and control lines there. Let's take a closer look at what each of those parts are. The first one is, of course, the Ethernet network. Standard Ethernet network rules apply here. Cat5, 802.3, 10 base T, 100 base T, Ethernet network. The second part is this what we'll call the sync network. Now, the sync network is simply going from eNet 2 between the two controllers. And excuse me while I grab my spotlight here, and maybe I can point some of this stuff out a little differently. Our standard Ethernet port goes in through eNet 1 on each of the two controllers here, and then our sync or crossover cable goes between the two eNet 2 ports on the PAC S controllers. Then, of course, you have an Ethernet connection to the arbiter for monitoring and status, and an Ethernet connection to the I/O. The third part is power. So here what we see is, I'm not showing the power supplies on this screen for clarity, but essentially from the arbiter to the power supply switcher to each of the controllers. And this gives us the capability, again, of resetting each of these controllers as might be required as part of the commissioning process. Finally, serial communications. Again, a dedicated RS485 two-wire connection between the arbiter on one port of the arbiter that says controller 1 over to controller 1's serial 2 port, and then from the arbiter's controller 2 port over to controller 2's serial 2 port. Hopefully you're keeping up with all that. Okay, let's jump into a demo. What I have here is my demo panel, and of course I've got a laptop that I'm presenting from that is running PAC Project Pro. The pieces of PAC Project Pro I'll be running are PAC Control, PAC Display Pro, Runtime, and the PAC Redundancy Manager. I have two PAC S-1s. Here's the first one labeled Controller 1, and the second labeled Controller 2. I have one PAC R1 as I/O, indicated up here. Then I have the ROK. The ROK is a redundancy option kit, and the first component of that is this one right here. That's the arbiter. And the second is that redundant power supply switch. Again, not a power supply, just a power supply switch. So my power supplies are all down here along the bottom. So I have an Ethernet switch power, a switch for my arbiter power, my controller power, controller 1 and controller 2. I also have a power switch up here for my I/O, and then an overall panel power. So I'm assisted here by Ben Orchard, who's going to help me simulate some failures. And in doing so, he's essentially just going to move the controller power switch from on to off and back on position to simulate some failures. Now, the other parts of the panel, I have a potentiometer here, an analog meter over here. We're also got a temperature loop. It's a standard PID. For those of you familiar with Opto and our learning centers, this is just the PID loop simulator from our learning centers. That means it includes a temperature input and a small thermistor control output that allows me to heat the element to change the process variable or the temperature input. I also have on my rack here 8 discrete outputs, all AC outs, 4-channel, and I'll be using these to blink lights in a series, basically a circular fashion, and then while we switch the controllers from active to qualified backup, we can see those will continue to operate as if nothing happened. I have an analog output, a couple analog inputs, and finally a digital input here, which has got a little handoff auto or the MOA modules, so I can simulate an input. Okay, with that, I will start up my PAC display runtime. Let me get back to my mouse. And I'll share my main screen. Okay, on your screen you should see PAC Display Runtime Professional and PAC Redundancy Manager. If you're having any difficulty seeing the PAC Redundancy Manager, which is on the right side of the screen, remember you can click the orange arrow in the little toolbox there, and that'll collapse the control panel over so that you can see more of the screen. Okay, hopefully everybody is able to see everything. Okay, so here's my PAC display Runtime Professional. Basically, I just created one screen that kind of indicates what's going on in the controller and allows us to view the data as it switches from one controller to the next. Let me grab my pointer again. And over here, you can see my controller 1 is in green. That essentially means that controller 1 is currently active. I can see that same information over here in the PAC Redundancy Manager. Controller 2 in PAC display is currently red, which just simply means that it's not the active controller for me in runtime. But over here in Redundancy Manager, I can see it is indeed a qualified backup, and I'll explain what that means momentarily. Next, I have my temperature log interval at 5 seconds. What that is, that's a float variable that I can enter in, of course, from runtime that will be sent down to the controller that sets an interval of my timestamp here. What I'm doing is I'm reading my temperature from the PID input, the process variable, and I'm logging that to a table along with a time and date stamp, or a timestamp. So you can clearly see that every 5 seconds I'm capturing the data from the temperature input. I'll ask my trusty assistant to place his sweaty palm on the temperature input, and we should start seeing that data change. There we go. Now I can change the log interval, of course, by clicking on this. I'll go ahead and do that now. And we'll just put in, say, a 2-second delay, and we should see that change indicated here in my temperature logging. And there indeed it is. The second part is this lights interval. Now, the lights interval is simply how fast the lights are blinking across my outputs. Now, in this webinar, we don't have live video feed, so I've attempted to mimic the light movement within PAC display. But as you know, PAC display is communicating through a PC server, pulling back a lot of information, so it's not going to react as quickly as what we'll see in real time. But in any case, you can see that the lights are indeed moving around. I'll click on there, and let's go ahead and speed that up a little bit. There we go. Now the next thing I'll show you is a temperature control loop. I'll click on that, and I can see this is a new feature in PAC Display Runtime 9.0 where I didn't have to build this screen. It's automatically built for me. I just clicked on the toolbox and created a PID loop screen. And there I can see my loop. My current input is 82 degrees. That means Ben's palms were hotter than I expected. I'm going to set that back up to 85 for a set point, and we should see a corresponding change in the output. Indeed we do. It jumps to 100%, and you can see my set point change, and then the PID is activated now to reduce that error and try to achieve set point. All right, enough about PID. Okay, we have all the pieces together. The strategy is clearly running in controller 1. Now what we're going to do is simulate a failure. Now, before I simulate a failure, I just want to make sure that it's clear that controller 1 is indeed running and controller 2 is set up as a qualified backup. When Ben flicks the switch and turns off the power to controller 1, you'll see controller 2 take over. You'll also see, after a slight delay, PAC Display Runtime switch over to controller 2. Let me get my highlighter up, or my spotlight. And this is what we're looking for right over here. That's going to be the fastest function that we'll see. Go ahead, Ben. Okay, you just click the switch. We see controller 1 went into a failed state, failed, possibly active. Essentially, that means that the arbiter cannot communicate with controller. Well, the controller's power is down. But what we did see over here in PAC Display is display now has moved over to controller 2. And indeed, all of our information is still the same. The table is, all this information is now coming from controller 2, but it's all synchronized with controller 1. So our temperature log interval and our lights interval are all the same. Okay, now the next step is I'm going to reapply power, or I'm going to ask Ben to reapply power to controller 1. Now when I do this, you're going to see a series of changes to the controller 1 dialog, this area right in here. And basically what you want to keep an eye on is this status via arbiter. Because here's what happens. The arbiter is continuously communicating to both controllers. It's not getting a response from controller 1. It is getting a response from controller 2. And we have indeed failed over to controller 2 and have an operating system. Now, when we reapply power to controller 1, what's going to happen is the arbiter is going to, again, keep sending these heartbeat requests and start getting some feedback from controller 1 as it powers up. And it's going to do 3 main things. The first is, controller 1, do you have the right firmware as the same firmware as controller 2? Step 2, do you have the same strategy as controller 2? And step 3, can you communicate to I/O as controller 2 is doing? If all of those tests pass, controller 1 will go into a qualified backup state. Okay, let's see how that works. Ben, we'll reapply power to controller 1. Okay, he's applied power. There it goes, non-qualified backup, qualified backup. Pretty quickly goes through those steps. So one of the questions we get a lot is, first of all, on a failure, how fast can you fail over from one controller to the other? Our bench tests have recorded speeds as fast as 50 milliseconds, so very fast. But of course, that's dependent upon many factors, including the size of your program, the number of I/O, and the number of redundant persistent variables, which I'll explain in a moment. So now we're in a state where we have controller 1 as active and controller 2 as the active controller and controller 1 as qualified backup. Notice that one of the controllers isn't considered master and the other secondary or backup or anything like that. The roles have flip-flopped, and it doesn't matter. Either controller can be active and either controller can be qualified backup. This gives you a lot of flexibility, as I indicated earlier, where now I could perhaps perform some maintenance or download another strategy to controller 1 while it's in its backup mode, leaving controller 2 active. Okay, let's paint a slightly different scenario for you. Now I have controller 1 that is, again, qualified backup state. Controller 2 is active. We're going to remove power to controller 2 and watch as the system corrects itself. Okay, Ben just clicked off power to controller 2. We go through the same series of steps. Controller 1 is now the active controller, and we'll see after a short delay PAC Display Runtime Professional switching back. And again, to be clear, PAC Display Runtime Professional is showing a delay as the OPC tags are realigned to the new controller, but in fact, the strategy has switched over very quickly, again, in the millisecond range, or tens of millisecond range on the hardware itself. Now, the other thing you'll see here is redundant system. The system is not in an ideal state, just means there's no qualified backup. Again, another status point there. Okay, the second scenario is this. The controller 2 has failed because Ben removed power. But let's say that the controller indeed failed, and we had to replace it with a brand new controller. Going back to those same 3 steps, let's say we put a brand new controller in there. The 3 steps are a little different. For example, we'll place the new controller in. The arbiter will query both controllers and recognize that controller 2, being a brand new controller, does not have a firmware match. So here's what happens. It instructs controller 1 in this case to copy its firmware over the sync network, so across the crossover cable on eNet 2s. When it does so, the arbiter will recognize that the firmware has been transferred over, will install the firmware, and force a hard reset. So now the system comes back up again, arbiter queries, and again asks controller 2, do you have the right strategy? Well, in this scenario, it wouldn't have the right strategy because it's a new controller. So again, it instructs controller 1, in this case, to move the strategy over the sync network and then bring it up into a power-up state. Okay? And then the third part is the arbiter will now say, controller 2, can you communicate to I/O? If indeed it can, boom, it moves into a qualified state. So while we haven't, while we don't have a fresh controller that we're plugging into our rack right now, I'll ask Ben to go ahead and reapply power to controller 2, and we'll watch those steps kind of go through again here. Now, once this has occurred, and this comes back into qualified backup, it's important to note that now the 2 controllers are in lockstep. Okay? And the way that that happens is through synchronization blocks in transactional charts. back in PAC Control. So let's go take a look at that. All right, let me share my So moving on our presentation, let's talk about PAC Control and our redundant control strategy. Now, a redundant control strategy is very, very similar to a standard PAC Control strategy with these exceptions or differences. First, a redundant control engine is configured in the strategy, and I'll show you where that's done. Second, the redundant control strategy has persistent redundant variables. Again, I'll explain that when I show you PAC Control. And third, the control strategy has one or more transactional charts. Okay, so what's a transactional chart? As you know, and different than, say, a PLC, a PAC Control and a controller, when it's communicating to I/O or variables, when it encounters a command to do a write or to write to a variable or write to I/O, whatever, it does it immediately, as opposed to, say, a PLC, which scans inputs, solves logic, then sets outputs. So what a transactional chart does is essentially bring a scan, solve, set to a chart. In other words, creating small transactions within a chart. And this gives you a lot of manageability relative to system performance and to keep overhead low relative to the synchronization between the two controllers. So a chart that has a sync block, which is indicated by this graphic over here on the side, turns a traditional chart into a transactional chart, and thereby breaks down the logic into these transactions. Now, once a sync block is encountered, all persistent redundant variables are written to, and all outputs are written to as well. So let's take a look at PAC Control. I close down my Runtime Professional, bring up PAC Control Professional, and hopefully you can see my screen okay. Let's take a quick whirlwind tour of PAC Control Professional with redundancy option. First of all, in terms of the options themselves, if we go to Strategy Options, click over here to Redundancy, you can see that controller redundancy support is enabled. Once that's enabled, you'll now see a block up here on the toolbar called the Sync Block tool. And of course, you can see several sync blocks in one of my charts here. Let's go on to control engines. You see here it says redundant controller pair. This is different than the standard PAC Control and a standard PAC Control strategy in that you actually configure controllers as a pair. This is the control engine configuration dialog. We can see that we're setting up for redundant controllers here. We have controller 1 address, controller 2 address, and the arbiter address. So when we configure a control engine, we're actually configuring two controllers at once. Let's move down to charts. As you can see, I have a various number of charts in my strategy here. Charts that have sync blocks, as I indicated earlier, are transactional charts. Charts that don't have sync blocks are standard charts. And thereby, as long as there's no I/O or anything being written to, no synchronization needs to occur. Let's go back to my redundancy example chart. Now let's go down to numeric variables. You'll see how I name my variables here. FP is a float persistent, which is a float persistent redundant, and then ones that don't have the P on them are just standard variables. So you can use a mix of redundant persistent variables along with standard variables, and there's a lot of reasons for that. One of them, of course, is to manage system performance. Let's take a look at this variable first, and we can see now when the redundant function is turned on within PAC Control, I now have persistent redundant as a choice for my variable. That means this variable will be synchronized between the two controllers. Now, another example of a variable is the end status trash. For those who used PAC Control in the past, you probably use some trash variable to move data that you really don't care about, such as the starting of a chart or whatnot. In this case, I don't need to have that synchronized between the two controllers. So I just choose Initialize on Strategy Run. And this is important again because it allows you to identify various instances within the controller, objects I should say, that will be synchronized between the two controllers, and others that don't need to be synchronized I can leave as a standard variable. Okay, moving down to I/O. I/O is pretty standard. Again, we don't support redundant I/O, so in this case we simply have created an I/O unit. It has its points, and of course it also supports PID. Now, let's take a little closer look at this synchronization chart. This is an example chart that's included also with the documentation and will be included with the SNAP PAC redundancy demo that essentially shows how you might take logic and break it up into transactions. And let's focus on the most important things, and that is where a sync block occurs is where points will be written to, output specifically, and redundant persistent variables will be synchronized and written to. Then you start other logic as you blink through, and then you synchronize again, which does the same thing. So this is a transaction. These three blocks is considered a transaction. Now then, if in the event that a controller fails, the other purpose of the sync block and these transactions is to indicate to the backup controller where to begin in the strategy. So if controller 1 fails and it was somewhere, say here on stop conveyor, then what would happen is as the backup controller took over, it would start again from the last sync block. Okay, let's go back to the PowerPoint for a couple of closing slides. It's important to understand a couple of transactional chart constraints. Basically, what you want to keep in mind is that you never want to end a chart without committing the transactions. There's some other things in there you want to be aware of, called charts and subroutines and counters and so on. But rather than go into detail of each of these in this presentation, I highly recommend viewing our SNAP PAC Systems Redundancy Option Users Guide, Form 1831. It is available on our website, so you can look at it and review. It's going to go over much of what I covered here, but of course get into a fair amount of detail. It's a 60-page document. It's worth reading. It spells everything out very clearly. There's also a data sheet on the SNAP PAC Redundancy Option Kit, those items, hardware items I discussed earlier, including the arbiter and the remote power supply switch. That's a Form 1901. Also, we'll be archiving this webinar so that you can listen to it at another time as an archived version. But also, feel free to dial in to Opto at 800-321-6786 and request a demonstration. We'd be happy to demo the redundancy option with you personally over this same technology that we're using for this webinar. And with that, I think we can take some questions. Alexia, are you still online?
I am. We do have a question from Michael, and he wanted to know, what happens if controller 1 had a comm failure with the redundancy manager and doesn't go inactive?
That's a great question, Michael. And the way that works is if you lose communications via Ethernet to, say, controller 1 is the example that you provided, the controller 2 will automatically take over. So what happens is controller 1 knows it lost its network connection, and the arbiter is, during its heartbeat request, gets that information and automatically switches over. So you're right in that the controller is still running, but it's not a qualified backup any longer. And the reason is because it can no longer communicate with I/O, because the I/O is on the Ethernet network. So in that particular instance, what we'll see is in the redundancy manager, we'll see that controller 2 becomes active, controller 1 goes to backup but unqualified. It's called non-qualified backup. Hopefully that answers your question.
Okay, Sean has a question. Is there any sort of code inside the sync blocks, or do they just have an inherent function by being there?
Great question, Sean. Yes, I didn't double-click within a sync block. No, there is no code within a sync block. It simply indicates when the transaction ends, and when, of course, the logic encounters that block, writes to I/O, writes to variables. Next question.
I'm not seeing anymore. So last chance to ask questions here. Of course, you can always call us or email us to get more questions answered. Okay, we have another one coming in from Eric. Is the redundancy only available with PAC Project Professional, or can it be done with PAC Project Basic?
SNAP PAC redundancy is only available with PAC Project Pro. At $9.95 list, still one of the best deals in the marketplace for control software, and includes, of course, everything you need, PAC display runtime, and OPC server.
Right, and I'll add that, I'll add that you do need, of course, the 9.0 firmware. If you're not doing redundancy, you can use 8.5 firmware, but you do need 9.0.
That's a great point. Now, the other thing you'll need to remember is the SNAP PAC-ROK, which is the hardware pieces that complete the hardware parts of the system.
Michael had a follow-up question to the first question. So Controller 1 may think it's still active, but Controller 2 will override?
Yes, because Controller 2 won't think it's active because it's gone into a non-qualified state. The Controller 1 in this case is intelligent to recognize that it no longer has network communications. It can't communicate to I/O. So it reports that back to the arbiter. The arbiter makes the decision to switch to Controller 2. So Controller 1 is still active, and then it's still active, but in a I shouldn't say active. I should say it's in a non-qualified backup state. So if you reinsert the Ethernet connection back into Controller 1 will say, hey, I'm back up, and it'll go into a backup qualified state.
Okay, and Christian wanted to know what happens if there's a synchronization error.
What happens if there's a synchronization error?
And I'm not sure synchronization between what, so maybe you can...
That was Christian?
Right.
Let's see if I can just unmute Christian.
You should be able to. If he's got a microphone, he can talk.
If he does, Christian, can you talk? Okay, he may not have a microphone.
Okay, we'll let him chat. No, he doesn't. So you'll have to follow up on chat, or you can give us a call. We do have one more question. Is 9.0 officially released yet? And yes, it has been released. It's available on the website.
Yes, and to reemphasize what Alexi had just talked about, PAC Control 9 is indeed available. If you're using redundancy, you'll need the firmware 9.0, and you want to put that, of course, in your controllers, and you must put that in your I/O systems as well. If you wish to use a lot of the features of PAC Control 9, and believe me, there are plenty, and there's some, as you probably saw in PAC Control 9 that I was just demonstrating, there's a lot of nice new features in it. You can use that software without redundancy, and we recommend using firmware 8.5D, as in Delta, which is also available on our website.
Okay, following up on Michael's, I understand it's a little bit hard to ask these questions, and I wish that, I don't know if Michael has a microphone, but I'll repeat his question because it's still not quite what he's looking for. Controller 1 thinks it's active, but the ROK switches to Controller 2 because it can't see Controller 1 anymore. Who controls the I/O?
Okay, let's see if I understand that correctly, because just because we lost the Ethernet connection doesn't mean the arbiter can't see Controller 1 any longer. Remember, the only communications between the arbiter and the controllers is over the serial network. The Ethernet network is not used for communications between the arbiter and the controllers. So if Controller 1 loses its Ethernet connection, the arbiter is still communicating with Controller 1 over the serial link and knows that its status is that it's not on the network and it can't communicate with I/O. And the arbiter now knows this because of the serial link and moves the active controller to Controller 2.
Oh, he's saying, what if the serial goes down?
If the serial goes down, a good question. That's a good question. If the serial goes down, then the arbiter will say, hey, I can't communicate. I have no idea what the status is of Controller 1 because I've lost communications with it. So if it's not active, that's a great question, because if it loses a serial connection, is the Controller 1 now realize it's lost its serial connection and then stops communicating with I/O? A good question, one I don't know the answer to. We'll have to figure that out. I would suspect that that it would. Because the whole point behind the arbiter is to prevent multiple masters to one I/O system. That's, in essence, what it's really designed to achieve, is to prevent two masters from communicating to one set of I/O. And then as a result of that, we were able to do many other things, and that's where we were able to manage firmware, manage strategies, arbitrate who's doing what. But in essence, that's the main task of the arbiter.
I can tell everybody is thinking these through because they're coming up with all kinds of permutations for you here, Benson.
That's fine.
What happens if the crossover link fails for some reason and you get a synchronization error?
Same thing. If the link between the two controllers is lost, then you don't have a redundant system anymore, but you still have a functioning system. Remember that it's a single point of failure at a controller level. So as long as one controller is active, you have a functioning system. If you lose the sync network, then you're not synchronizing any longer, and then the redundancy manager will say, whoa, the system is not in an ideal state. It's not redundant any longer. Still functioning, but not redundant any longer.
Okay, another one. Is the serial connection connected between the two PAC-R ones for the redundancy? I think maybe he means the two PAC S's.
Mm-hmm. Because PAC-Rs are not supported for controller-level redundancy. So the serial link between the two PAC S controllers. Is that the question, Alexa?
I think. Is the serial connection connected between the two PAC S for the redundancy?
No, they're not. The connection between the arbiter and the two controllers are two independent serial links.
Right, because the two PAC S's aren't connected serially. They're connected.
That's correct.
Ethernet crossover.
They're only connected Ethernet crossover, right? And they're also connected on the network. I mean, right. Remember, it has two Ethernet ports. One Ethernet port is used for standard Ethernet connectivity. The second Ethernet port on the PAC S controllers is used for the sync network. Let me bring up the...
While you're doing that, he's asking also, would you use a PAC S1 in a redundancy setup? And yes, you need a PAC S1 or S2 or S1 or 2 wireless controllers. As Benson said, the PAC-Rs are not supported as redundant controllers.
Okay, I have a screen up. Hopefully you can see that okay. Actually, let me just go ahead and make that full screen. Okay, once again, this kind of gives you an idea of how the wiring is done and how the, well, I should say what the connections are. Let me actually advance to another screen here. Pull out my highlighter once again. I know it's easy to kind of go through all this initially, and then once you see it working, you're like, whoa, wait a minute, how was that connected? So here we go, just to recap. Independent serial lines from the arbiter to each controller. Supply voltage lines from the arbiter to the power supply switcher, which in essence interrupts power. This is basically a normally closed contact, and it just opens the contact, closes it again, which initiates a reset, a hard reset of each controller. Ethernet network over ENET1 of both controllers, the PC, and the I/O. And finally, the Ethernet crossover cable between the two ENET. Now, one thing I should mention is that this information that goes over this crossover cable network is very, very high speed. It's not TCP IP. It's essentially down at the MAC level. So this communication is very, very fast and not subject to normal TCP overhead that you would find on a standard Ethernet network. That said, it's just Cat5. So it's not a special cable that's required, and we found no benefit to going to, say, with a fiber link between these two, as we've seen from some other redundant systems that are on the marketplace.
Okay, can G4 Mystic I/O multi-drop across both controllers?
Multi-drop? No, and the reason is G4 Mystic I/O is serial. So right. Serial I/O is not supported with the redundancy option kit.
Okay. And Patrick is asking to be as close to bumpless as possible. Are the placement of your sync blocks after a series of commands or arbitrary placement?
They're not arbitrary placement. Again, what happens is you have a sync block that indicates the end of a transaction, then the beginning of a new transaction with the next block that does a write to variables or a write to outputs of I/O. So you could have a lot of other blocks that do various things that don't write to I/O or write to variables. The transaction hasn't started yet. So basically what you're doing is you're batching up these writes at the first encounter of a write. And then when it hits a sync block, that is batched sequentially and all the writes are made. So it's not arbitrary. It's based on how you want to construct your program logic. And remember, this is for each chart. Let's talk about quickly what happens when when a synchronization occurs. Let me go to this screen here. And just to clarify, it's always best practice to use transactional charts in a redundant strategy. You don't need to do so on a power-up chart, but for everywhere else, it's always best practice. So when a sync block is encountered, the data generated by the chart between the sync block and the previous sync block is synchronized in both the active and backup controllers. The sync block also indicates, as I said earlier, to the backup controller what state the chart is in and where in the logic to begin in case the active controller fails. Now, when a sync block is placed in a chart, thereby making it a transactional chart, it tells the controller not to do any writes in that chart, not to do any writes to any variables or any outputs until the next sync block is encountered. One other thing, all redundant variables and I/O changes are synchronized no matter where the change or update is initiated. For example, a change could be initiated in, of course, a running chart. It could be in debug mode in PAC Control. If you write to an I/O or write to a variable, all the variables and I/Os are updated, or an operator change made from PAC display. So when I entered in from 5 seconds down to 2 seconds, that action made a synchronization occur. So synchronizations occur in a number of different ways, either through the sync block or a changing of that from something external like PAC Control or PAC display runtime. One final point on that is that all of the points are written to and all of the variables are updated when encountering a sync block or those other reasons why a synchronization might occur. And then finally, only the change stuff is synchronized. So if you have a whole bunch of redundant variables and a whole bunch of I/O, the controller, the redundancy scheme that's running in the controllers is intelligent to identify which variables and which I/O have changed, and only those are synchronized.
You read his mind and you answered the question right as it came in.
Oh, I should
Great.
look at the questions.
No. Christian was asking it at that very question right as you were talking about it. So
oh, okay.
It was good timing. Good points. These are great questions. Any more?
Absolutely.
All right. I think that's. Oh wait, nope. Got another one.
Somebody's typing feverishly.
Our good friend Sean is asking, can a large number of sync blocks start to degrade overall system performance, or is this a non-issue?
That's a great question, and the answer is yes. And that's the point of the sync blocks and the use of redundant variables and so on, is the more sync blocks you have, the more redundant variables you have, the more there's system overhead, and that will result in degradation in overall system performance over time. So yeah, you want to be judicious in your use of sync blocks, as well as being, as I said earlier, relatively judicious with your persistent and redundant variables. So all of those things will affect performance. I don't have any data that indicates where that point is. At least I don't have it on me, but that's one of the reasons why we approached redundancy in this manner, is so that was manageable. So as your program grew in size or complexity, you could manage, you balance, let's say, the synchronization with the performance of the system.
Okay, nothing else at the moment. We'll give everybody else a second to type in any questions they might have.
Remember, you can go to the Opto 22 website and request system engineer help, or just send an email to systemseng@opto22.com, and we'd be happy to respond the best we can to your questions about the redundancy option kit.
Okay, thanks for attending, and thanks for your time too, Benson.